Let's add a custom construct for our IAM roles. We'll do it in a new file, named it im.py. It is going to be construct, so we can copy this line from here and use it in the new file. Okay, looks good. Next is to import the IAM role submodule from the inputs.aws. It's IAM_role. This one. And we input the IAM role class. Great. Now the class can be defined, which inherits from construct, of course. The dunder init with the self, scope, and name. Next, initialize the parent class. Super. Dunder init. And passing scope and ID. Okay. Now the IAM role object can be defined. Let's check this IAM role submodule for params and attributes. So this is the submodule. Here's the class. Okay, let's check which are required params here. The scope and ID, a SIM role policy is required, which makes sense. And these are all required params. Okay, this submodule represents this TF resource. Okay, let's check it. This is TF's page for this resource. It has several usage examples. Let's follow this example. The role references this data resource, which is defined here. So the required assume role policy references the IAM policy document, which presents the opportunity to explore the data IAM policy document submodule as well. Let's find the data IAM policy document submodule here. So here's the construct. To be imported from this submodule. All right, what are the required params for this class? Nothing more than the ever-present scope and ID. The class represents this TF resource. Which has nothing more than the expected IAM policy statements. Okay, let's input the data AWS IAM policy document. AWS IAM policy document, this one, and input the class. Okay, next, instantiate a policy document object. It equals the data in policy document, passing self as scope, and copy the vars name to be used as the ID. Next, define a statement This is a list of elements to comprise an IAM policy. Okay. This is the first element of the policy. Next is effect. So allow then principles. It's yet another list with identifiers. This is task.nws.com. And the type, which is service. Okay. We get actions and effect, principals, L here, identifiers and type. Okay. Next is to create the role object. Equals IAM role. This class, pass scope. Copy this var as its name. And the assume role policy attribute assigned with the document policy object. This one is in a JSON format and will need the on attribute. Okay. This is the custom IAM roles construct. Let's use it in main. Now the my IAM roles construct can be imported and used in main. Let's define the roles in a dedicated stack. My IAM stack inherits from the Terraform stack, of course. Done the init with self, scope and ID. Then initialize the parent class. The first thing is to set up a provider. Let's copy it from here together with vars and change the ID to IAM_stack. Now I can create a role object. Task exec role equals my IAM roles, pass the self and the name. Okay, this is the stack. Next is to add this new stack to the app. IAM stack app, call it project IAM. Okay, let's save the changes. Check for any syntax errors with cdktf synth. No errors, great. Let's deploy this stack. Okay, here's the policy. Got all the elements. Looks good. Approve. The role and the policy are created. I want to use this role in the my stack to pass it to the ECS task objects. So the role has to be referenced cross stack. Let's check how to do that. HashiCorp provides this cross-stack reference example. It isn't very detailed, but some interesting information is here. Accessing a value from a different stack causes it to be exported as a Terraform output in the origin stack. This value is then accessed through a remote state in the target stack. Both are added to the respective stacks automatically. Looking at the example, the VPC stack is the origin object. This stack here is the producer, and the destination is the backend stack. This one is the consumer, and the values, this and the others, are passed via the backend stack config. And this is the backstack config class. Python doesn't have an interface structure like TypeScript has. Here, the backend stack config is an interface. In Python, we define a class to act as an interface. Let's give it a try. Let's assign this instance of the myIAM stack to an object. Next, add the config class. Initialize it to take the task exec role. And I add the self ECS task exec role var task exec role. Now an instance of this class can be passed as an argument to the myStack construct. Next, a new var can be added. And assigned with the config.ecs task exec role. And this role can be passed as an argument to the ECS task objects. So this config class has to be passed to the consumer stack. Let's add it to the myStack instance here as an argument and assign this one with the config_IAM object ECS task exec role var and the exec role object from the IAM construct. In the ECS task dev construct, add the task exec role param, add the var exec role equals task exec role. Next, add execution role on to the ECS task definition instance. Oh, let's add the on suffix for better clarity. And this one, oh, it's self. Okay, let's save the changes and check for any errors. cdktf synth. No errors, great. Let's deploy these tags. Here we go. Cross-stack output cdktf has created for us. Fantastic. cdktf has indeed created the cross-stack reference outputs in the project YIM stack. Okay, let's approve this plan and see what's next. Okay, let's check what we've got. Okay, here's the cross-stack output. And the project Y stack has got the cluster and the tasks with the IAM role. Great, looks good. Fantastic, it has deployed the stacks. These are the defined outputs from the project Y. And this one is automatically added cross-stack output in project YIM. Great. Let's have a look at the cdk.tf.json files of both stacks. This one is the project YIM stack. And we are checking for outputs. And here's the cross-stack output that was added by cdktf automatically. This output isn't in the code. The myIM stack doesn't have any outputs. Neither has the IAM custom construct. However, the cdk.tf.json has it. So cdktf does automatically add cross-stack output. Next, let's examine the project's Y's cdk.tf.json file. And here is the added Terraform remote state definition, which points to the project YIM state. This is how the cross-stack reference is implemented. cdktf adds outputs and the remote state to respective stacks to make the reference seamless.